that did it. Let's see. Okay. Good morning. Buenos dias. And that's the totality of my Spanish. Although that's not really true. I know a few more words I'll try to say during the talk, especially if they're jokes that no one gets. So I entitled this talk, Nanotechnology's Application and Impact Over the Next Decade. And it really is a bit of a survey. It's a survey that comes from my point of view as a nanotechnologist for the past many years. And it's also got some information just generically about nanotechnology, what's going on from a sense of the United States and its position in the world, which I know about. So that'll give you an idea of what's going on. And then it's also got a couple of examples of nanotechnology in that are interesting to me. One is from my company, Nantero, which I thought people would be interested in. And then lastly, it's got just a couple of questions and perhaps some potential roadblocks for nanotechnology, which the group here might want to discuss and really find some solutions to, perhaps. I think these are some fundamental things that you'll find of interest. And during the talk, feel free to interrupt, make this more of a discussion. We have quite a long time to do this. People can ask questions, and Case is laughing already. And you can even disagree with me, because I have my own opinions, and sometimes people don't like them. Okay, this is just who I am. I have my PhD in chemistry from Harvard University. I think chemistry is sort of one of the fundamental tenets of nanotechnology. In fact, when I think of nanotechnology, I always say, well, it's just chemistry, and the physicists immediately disagree. But I started a company called Nantero, and the idea of the company was to make a new form of computer memory. When you go and turn on your computer, the very first thing you do is nothing. You just wait. And you wait while your hard disk drive takes its programs and loads them into the DRAM. Once that's all done, then you can actually start to play with your computer. So these three characters, me being in the middle there, got the idea while we were at Harvard of developing a new type of memory system which would allow this computer to have so-called instant on. Hit the start button and immediately it would go on. And this has achieved some accolades. We were in IEEE Spectrum's top 10 companies and Scientific American, and have raised quite a bit of money from the venture community with some very nice additional accolades, like a lot of patents and that sort of thing. So that's who I am, sort of the credentials there. And now we start at the beginning, and the beginning of nanotechnology. So first, what exactly are the sizes of things? And we like to think about things that are natural first on the left-hand side, and these are some of the sizes of these things. Human hair, something around 100 microns. People are pretty familiar with what that is. That's pretty small. Here's some red blood cells, which are about 10 microns. People often talk about medical applications, and they talk about cells. And I say, you know, cells are really big compared to nanotechnology. I mean, 10 microns is quite large. And here's a dust mite, perhaps not a good thing to find too often. Then we get down into, we shrink a little bit, get down to nano things. And so here's a protein, which is 10 nanometers in diameter. In chemistry terms, we like to call this 100 angstroms, so you might hear me talk about angstroms. Here's a DNA molecule, and people often say to me, well, this nanotechnology, you know, I don't use it. And I say, well, look, you've got something in your body right now which is 2.5 nanometers in diameter, 25 angstroms, with a macroscopic length. You use it every day. And I said, well, what's that? There it is, DNA. So we're all utilizing that all the time. We're all nanotech machines, if you will. And here's some atoms of silicon. You see these are down into just the 1 nanometer diameter. These are the sorts of things that you find in computer chips. I also can find atoms of silicon sand, silicon dioxide. So does anybody want to say anything about that? Does anybody have any nanotech things that they're unsure about? They want to say, do you think that's nanotech? So here are man-made things, and here's a head of a pin, 1 to 2 millimeters. Here are some MEMS machines. These are microelectromechanical machines that people have made, which are microstructure. Those aren't even nano, but we would consider them incredibly small by most people's standards. And then you get down into things like carbon nanotubes. And carbon nanotubes are a small material that's made all out of carbon. Take a sheet of graphite, roll it up into a cylinder. It's 10 angstroms in diameter with a macroscopic length. So I like to say, well, carbon nanotubes and DNA are pretty similar. And there's the man-made thing, and there's the natural thing. Here is, I think this is a little quantum coral that was, I'm not sure, maybe that was done by IBM. Is that an IBM thing? Okay, good. So I think it has a bunch of coppers all aligned in a certain fashion. And here is a buckyball. And you might have heard about Buckminster fullerene. There was a Nobel Prize given for its discovery. Rick Smalley, who was the discoverer of Buckminster fullerene, passed away recently, which was a very big sadness in the nanotechnology community. And so we honor him. So this gives you an idea of the sizes of things. Anybody want to say anything about that? The sizes? Chris, you want to make a comment about the sizes? Are you amazed by how things that you thought were big are actually not so big? Things that you thought were small, not so small?
And that we can apply these same scales to the things we're working on. Any thoughts about it, or are we comfortable so far?
Okay. Yeah, feel free to interrupt. I want to make this into a discussion. Case, say something about this. Are you struck by this? When I first put all this up, I was struck by it.
Basically, what you could say, everything around us is made out of atoms and molecules anyway. So the question is, isn't everything nanotechnology? Because, molecules make up everything. So it's been there since the beginning of time. But at the same time, so what makes the difference? And I think that's the right figure here, that up till like 20 years ago, we were able to explain what we see in our macroscopic world by trying to understand the nano world and trying to explain our macroscopic world on the basis of quantum mechanics and all these fancy things. And nowadays, we were able to control that world. And I think that's the big, big difference between 20 years ago and today. We opened up that black box of atoms, I think.
And that brings me nicely into my next slide, which is, so what happened? How did this happen? What's changed? If we've had chemistry around, we've had all these things, what's gone on? And what's gone on is we got a whole bunch of tools. So the tool makers and the advanced researchers gave us a whole bunch of new toys in which we could look down at a certain scale. Okay? And here's an example of probably one of the most important tools, focused ion beam. Well, that sounds bad. If you have one of those in your living room, you better watch out. I know a guy who has one in his living room, by the way. Scanning electron microscope. And what this really does is it lets you look at the structure of things down at the atomic level, and the focused ion beam is sort of a nanoscopic knife, if you will. You can use actual molecular species to cut things and look at them inside of a high vacuum chamber and get an idea of what they're looking like. Here's something called Ebm Lithography. I'm not going to say too much about lithography because we're going to hear about probably some of the best lithography in the world. But the idea here is using a tool like Ebm Lithography, one can actually make small structures. You can outline different kinds of lines and patterns and whatnot and make devices that are down at the 5, 10, 20, 50 nanometer scale using various techniques. And those type of techniques allowed us to start to make things that are of interest. Here's scanning probe microscopy, another tool that people are very interested in. Some of these tools let us measure the heights of different types of nanoscopic elements. And here's a deposition tool. This is another vacuum tool, plasma-enhanced chemical vapor deposition. And this is good for growing carbon nanotubes, for example, in a vacuum chamber. So we have new tools for not only exploration, but also for growth of these things, generating new types of structures. So this is the big change. This is what really happened in the past 20 years that got things going. And then you might say, okay, so we have some new tools. I know the sizes. What is it? What is this nanotechnology? And let's get into that a little bit. So first, people define nanotechnology in various ways. Here's one way, based on dimension. And we're going to hear from at least one or two speakers today on nanotechnology based on dimension. And that means fabricating things that are of a nanoscale. And this tends to start big and get smaller and smaller and smaller. And you make different types of copies of things and shrink them down. And that's based just on dimension and just on fabrication. Then there are people who actually manipulate atoms. This is the second definition, is based on the method in which you fabricate. So instead of shrinking the same thing down, now you're going to take individual atoms, you're going to move them around, you're going to put them where you want them, and you're going to make things exactly where you want. They call this bottoms-up assembly. And this is another definition of nanotechnology, and you'll see people talking about it. They think, you might think they're talking about this, they're talking about this. So yet another way of looking at it. And then a third way, and this is one of my favorite ways, and several speakers are going to address this, is based on principles of operation. So what that means is that if you have nanoscopic materials and you let them interact with surfaces, different things happen, special things happen, and it only happens in this certain size regime. And so that's another definition of nanotechnology, where these molecular forces, probably everyone had to take chemistry in high school, I think. Did anybody not take chemistry in high school? You might have forgotten all of it, but I think you had to. Who took chemistry in high school? That doesn't count. Okay, well, most people had to take it and probably tried to forget about it. But when, of course, I love chemistry, but when you took chemistry, one of the fundamental things we learn about are molecular forces. And some of the molecular forces, for example, called dispersion forces, are sort of told in a dry way. You know, people don't find them very interesting. It turns out they're very important. Dispersion forces, for example, are the thing that keeps a drop of water together. Hydrogen bonding, the water molecules themselves all line up in such a way that they would rather be near each other than spread all over the place. That's a pretty fundamental force that we deal with. Nanotechnology, that kind of dispersion force, is enormously powerful, and we can utilize that to make things. Okay, so this comes from the Defense Advanced Research Projects Agency, DARPA, and this is their definition of nanoelectronics. No, that's kidding. This is not what it is. Nanoelectronics is not this. Come on, it's early morning, but let's have a little more of a chuckle. Jeez. I mean, you know, we called it the nano-banana. Anyway, I thought that's supposed to wake you up. But a lot of people, you'd be surprised, people even at fairly high levels in the government have become confused about what is going on in nanotechnology. Oh, nanoelectronics. Well, that looks good, Chiquita. Okay. So here's one of the definitions of nanotechnology, which is the one based on scaling. So we say, for example, we start in 2003. Here's a 90 nanometer CMOS scaling of a transistor. Here's a transistor here. I won't go into how a transistor works, so maybe somebody else will go into that. No, I'm not going to talk about that. Am I stealing any thunder, Dario? Okay, good. So you can see here, though, they start at 90 nanometers. You go down to 65 nanometers. You scale down to 45 nanometers. Someone's made a 32 nanometer transistor as a prototype from 2001. A few years ago, they made this. Here is a prototype of an even smaller transistor down to 10 nanometers from 2003, and they continue to scale. And at some point, this scaling perhaps might meet a roadblock with standard materials. So one could imagine introducing some new materials, such as nanotubes, as I mentioned before, or nanowires, which are a close relative made of different materials other than carbon. And this is the dimension, based on dimension, the way you describe nanotechnology, just this scaling. So that gives you an idea of that. And then here's one that's based on fabrication. And this is really sort of the Feynman dream of nanotechnology, and the thing that probably concerns people the most if you ask them about nanotechnology. This is the sort of thing they find that concerns them. These are these nanotechnological machines. And you can see here, each atom in this is a different color, and it's defining a differential gear. Well, as a chemist, we have no idea how to make these things. I mean, these are really difficult structures to understand. But a lot of people, when they talk about nanotechnology, they think of nanomachines, they think of nanobots, they think of things getting into your bloodstream and crawling all around and growing explosively. I watch Star Trek, they have nanobots all over the place. Well, it turns out this is actually the hardest concept to imagine making in nanotechnology because it requires exquisite control of all the different atomic structures, and things based on fabrication of this sort are the hardest ones. We'll see some of those, but that's really tough stuff. Okay, now here is the one that I like the most, which is based on principles of operation. And as I talked about, these are things based on molecular forces. I talked about dispersion forces, hydrogen bonding. These are also part of something called the van der Waals forces. The Dutch are the gurus of these molecular forces. In fact, someone asked me last night, they said, which European country do you think is really doing the best or has the leadership position in nanotechnology? And I said Holland. I don't know what other people think, but I think they have taken a leadership position. And if you look at some of the research that's going on, you'll see there's quite a bit of research going on in Holland with molecular forces, people doing nanotechnology. And of course, the Germans are also doing very well, but there's quite a bit going on here. And some of these forces, though, they're not predictable. They're nonlinear. They are things happening that we didn't understand, we didn't expect, and they're non-intuitive. And we're going to hear several talks today of people who have discovered things that are nonlinear, non-intuitive. They happen at the nanoscale, and they provide vast possibilities for real development of products. So now, let's see.
Could you just go back to the last slide?
Annabelle.
Yeah, could you just...
Yes. I'm glad you interrupted.
What exactly is that?
So
How's it different than putting something together?
What this means is that when people talk about nanotechnology, they might be talking about things that are based on shrinking dimensions. They might be talking about putting together atoms, or they may just be talking about things that we know about already in chemistry or physics that have just special operation. That when you allow things to come close together and they're at a certain scale, the operation of them changes. So they may have different forces that are working on them that are special. And so when people talk about nanotechnology, you might not see anything there that looks particularly obvious, like a small atomic arrangement. And yet they mean nanotechnology because these forces are in play. And we're going to have at least one really good talk where you'll see special forces that have been isolated which do something interesting. Just part of the definitions. Please.
Isn't there going to be some kind of physical limit where you can push this where on the one hand you have a size limitation and then you have a non-linear behavior so that you cannot push the size down? For example, in the CMOS slide which you showed, how far down can you then go theoretically and without having the things fail due to a combination of these different forces?
Yeah, I think there'll be some discussion. Is there going to be some discussion of that topic? This is just the intro, so I'm whetting your appetite, and we have, I believe, 8 or 9 speakers who are going to address all sorts of different prospects here, including that one. And the answer is, I left the boxes open. I don't think we know yet. And it may be that there's going to be a combination of dimension plus atomic scale manipulation plus forces. All three of these things may be in concert to continue this scaling profile, for example, in CMOS. I picked CMOS because I'm a chemist who really likes semiconductors. Of course, if there are any physicists in the audience, which are the semiconducting elements? And anybody who can come up with a semiconducting element, see me afterwards. That's my, okay.
Thank you very much.
It might be helpful to give one example where the van der Waals forces or other nanoactive forces take over from the macro forces.
Annabelle, I'm going to show an example. I'm going to show it's not a movie, I'll show a still photo where these forces come into play. It's actually a photo of the action of a memory switch from Nantero. And I'll show you exactly how these forces are involved in making a memory switch. And is that good? Yeah. I haven't shown that before to you, Chris, but I don't think. But I think it's a good set of photos. You can see it in action. So now here, you might say, well, what companies are involved? You know, who's involved in nanotechnology? Which of my colleagues, which of my neighbors, which companies that I'm working with might be involved? And this is just to give you sort of a broad-based view of who's involved. All of these companies all make, in one form or another, a microscope or a tool that enables nanotechnology. And so I show this not to plug any of these companies, but so that you can see there's a broad base, there's a broad brush here of different companies, and you might see some of these companies in your work and say, oh, Carl Zeiss, for example, they're involved in nanotechnology. I didn't know that. And there are several European companies on here which you might know. And now, if you've got the tools, that enables all of these companies to do their work. And oh boy, now it's going to get interesting, because we've got a lot of different companies here. You look and you can find biotech companies, energy companies, semiconductor companies. There are a lot of different companies here doing nanotechnology, and this is just a small sampling of them. But I leave this up here. You might recognize some of these names, and you might say, well, this is a company I know, and they're involved with nanotechnology. Certainly some people probably know some of the bigger ones, like Texas Instruments, Chevron, GE. So these are just a small sampling, but it is nanotechnology. Okay, now get to, so what are people working on in nanotechnology? Now we have some idea of what it is. Anybody want to stop there and ask any more questions about the definitions and what it is we're working with?
Brent, I do have a question. I'm over here.
Oh.
And I would like to go back to an earlier comment about, those of
far?
us who did take chemistry in high school and did any basic chemical reactions, there is an impact at the molecule level, right?
Absolutely.
And you are affecting things that are of nano dimensions and affecting molecules and atoms. And of course, all the matter and all the things that we use, they are affected by those forces at the molecule and atom level. So what makes this any different from the work traditionally done in chemistry or what have you? I mean, I think I'm getting a sense, and your definitions do help, but I would like to address that once.
I think we're going to get into some of the specifics of what's different. And in many cases, if you go back, let me go back through this again, because I think this is important to kind of go over so people understand the definitions. So in this case, not much is different. It's more of the same, only less so. We're getting smaller. And we're taking things, this goes up, this curve goes straight up towards quarter micron, micron devices. So some of the same principles that we used in making electronics, for example, we're still using, and we're shrinking them, and we're understanding some aspects that are new, but primarily it's mostly the same, and we just refine and we get better. And when some people talk about nanotechnology, that's what they mean. I know that every time I give a talk and I'm standing next to an Intel person, they always get up and say, Intel is a $25 billion nanotechnology company. We're the largest nanotechnology company in the world. And this is what they mean. They mean, we do this. We do things based on dimension. So that's one form of nanotechnology. You hear that all the time. That's what they mean. Then in this one, this is really far out stuff. People aren't sure how to do it. They'd love to make nano gears and differential motors and all this sort of thing. They really don't know how to do it. It's based on fabrication. That's another definition of nanotechnology. And then this one is based on forces.
Brent, could I stop you there? Would you go back one slide?
Sure.
The vast majority of the scientific community thinks this is pure science fiction, that diagram there.
I agree.
There's no way that's going to happen. And you know very well that Smalley personally attacked the Foresight Institute on the basis of promoting this idea. That's not how chemistry works at all.
Absolutely. But you hear it, and people... So, Hank, I think my point is, let me make it more clear, is this is far out. But when people talk about the definitions of nanotechnology, they often erroneously describe things like nanobots, little robots flying around, and in fact, we don't know how to make these. But
I think we do a certain disservice to the scientific community and the business community if we mix in science fiction with real stuff.
But you've got to address, I think we've got to address what people hear. And so all I am trying to elucidate here is when people talk about these kinds of things, you will hear those, and that's what they mean, but that's not the only definition of nanotechnology, and we may not be able to make those things.
The whole cult associated with the Foresight Institute, I think we ought to call it what it is. It's a cult. It's a science fiction cult.
Assembly, though, because I think the concept on this slide is not so much the desktop nanofactory as and one that does...
Look, by putting that picture up there, you're implying that there's a machine exists that on a tabletop can do that.
No.
And that's totally out to lunch.
No, you're absolutely right. You're absolutely right. But this is, Hank, my point, and I'll say it again, is that these are the definitions that people hear, and so they need to have a differentiation between what we mean. And so you'll see people talk about this. We don't know how to make these, and I think that was my first statement, is we don't know how to make this stuff. Nobody understands this, but there are people who, when they talk about nanotechnology, will talk about it based on fabrication. They feel that they might be able to put these atoms together. As chemists, we don't know how to do that. I won't say it can't be done, because as Chris brings up, self-assembly, for example, is a technique, a bottoms-up technique, where complicated things get put together. And if we were to say that we could a priori design a protein and put it together, you might say I was crazy about that as well. You'd have to design amino acids. You'd have to design interactions between sulfohydryl groups, cysteines, for example, that have to go together, and yet it occurs. So this kind of thing is far-fetched. I don't think anybody's going to make this, but it's important for people to understand the definitions that are being used in the community, so you know this is one thing people talk about.
Hey, Brent, can you go back a slide?
Sure.
Hank, I actually think that Brent might be actually agreeing with you. If you actually read the spelling of the word dimension that he uses below, it actually has more to do with mental illness than it has to do with any physical reality. So perhaps we're just playing with labels here, Brent?
Carlos, that's a good one.
Brent, let me clarify. For those of us who are not in this scientific discipline, to understand better what you disagree with, is it just the picture of the science fiction machine, or is it the concept? I just want to clarify. Or is it the very concept of self-assembly? What's the science fiction part of that?
Because self-assembly is a process that's been well known, and in practice we do it in my own laboratory. We're called templated self-assembly. But I just wanted to point out that there exists a cult group, okay, called coming out of the. You're nodding your head.
Yeah, I know. I agree with you.
To point this out.
I agree with you.
That originates at the Foresight Institute, okay, and this is pure science fiction.
Absolutely.
Okay, and we ought to just call a spade a spade. That's all. Period.
I-
Let's go
I-
on to the
I
next
want-
slide. Let's
I-
go on to the next slide.
I want to
This
argue.
shouldn't hold up the discussion.
All right, I think most of the group doesn't know Eric Drexler or the Foresight Institute, but I think, so you're not maintaining a point of view different from.
No, oh no, I'm in
But I think
violent agreement.
I want Angel's question to be addressed, which is the difference from chemistry, and it seems to me, at least, not as a scientist, that the idea of self-assembly to get individual molecules to put themselves into a desired design is a difference from chemistry. Is that a fair statement?
No, that's what chemistry has been doing for centuries.
Absolutely.
That's what life does, okay? You can think of it, that's what happens in life.
Absolutely.
But
And
I really think we ought to go on, okay? Let's not get hung up on this, okay? Let's talk about science, okay?
Let's keep
and
going.
This picture is not science. This is
No.
pure fiction.
Absolutely. Yep, we're in violent agreement, Hank, but I thought it was important that people see the different kinds of things that are out there, because otherwise they might think that when they see this is all there is. This is what it's all about. And I want to make the
People,
point
when you
that
show
that's
that,
not.
they may think it's real. Look, you've got a tabletop, you've got an electrical outlet there, you've got a machine, as if that's being done. It's not true.
It's not true. It's not true. Okay, we'll move on.
The electrical power is not plugged in, if you notice that, so this may be a problem.
Well, I actually put that in purposefully to see if anybody would notice and make a nice argument about it. And I'm pretty happy, so. No, he's absolutely right. It's definitely true. Now we'll get into a little more reality here. So I think this is a long list, but this comes from the National Nanotechnology Initiative. And the point of this list is just to say these are areas in which people are interested in exploring nanotechnology. And some of you will find take away different things from this, but you see it's very diverse. They're all over the place. Here's healthcare, therapeutics, diagnostics. National Cancer Institute has an enormous program going on in the United States on cancer prevention, cancer cure, cancer diagnosis, and cancer treatment using nanoparticles and other materials. And I think we have several talks today on that field. There's going to be people talking about nanoparticles and nano manipulation for biological purposes. And this just gives you an idea of the diversity with which people are working. Nanoelectronics, photonics, that area will also be covered. So here's just a snapshot of some of the things people are working on. In medicine and health, IT, you might think, oh, IT, okay, that's nanoelectronics. Here's energy. Hydrogen fuel cells is an excellent example. Really, the chemistry of hydrogen fuel cells is something that people are exploring more and more. And having high surface area is important in getting good reactivity for hydrogen generation and storage. And here's some areas that you might not be thinking about. For example, food, water, and the environment. We're going to hear a talk about environmental conditioning using nanoparticles later. But there are several people, for example, using carbon nanotubes to purify water. And that's a huge problem all around the world. If you can purify water in remote places, it'd be fantastic. And then there are some new instruments, for example, which are coming out of nanotechnology as examples that could be even more valuable in the future that might give you new modes, new ways of looking at these things that will enhance our exploration of it even more. All right, so now I'm going to get into a few charts just to set the landscape of what's going on out there so you can see the scope of this thing and who's involved and whatnot. And here is investment in US dollars over time. And we'll start off with, this is the National Nanotech Initiative from the United States that's launched. And you see it's a couple $100 million. We're going to run out here. And the President of the United States signed a Nano Act. Apparently he used a very small pen, extremely small. It was just a joke. And I'm nervous about Hank saying, no, there's no such thing as a nano pen. Well, there actually is. Dip pen lithography is a technique from Northwestern. It really is a nano pen. But you can see the idea here is it built up and it's going up. And there's a lot of investment going on. People are very interested. And it's so important that the president actually signed an act that said, for the next 4 years, we're going to do nanotechnology. We're going to explore it. We're going to learn it. It's a big presidential act. And I think that's exciting. That really brings it to the forefront. People believe that it's important. Here's something about global investment. I think others are going to talk more about this, so I'm not going to cover too much. I think the point here is that here's the public money. So here's $4.5 billion was invested in 2004. And you see, this is, I think, the interesting part. It's split Asia, North America, Europe, relatively evenly. I think there's investment in all areas. People are excited about nanotechnology and are putting money into it. And then the other thing to take home from this, which I think is interesting, is that the private sector is also starting to put in a substantive amount of money. So they are investing in this. And here's something that's a curiosity within the United States that you might find interesting. Individual states within the United States are putting their own money in besides the money from the federal government. So they, even at the state levels, are getting excited about it. And then here's another measure of what's going on in nanotechnology, and this is number of patents here on the y-axis over time, and I've broken it out here. This source comes from Journal of Nanoparticle Research, where this fellow, Dr. Huang, looked just for nanotechnology in the word from the US Patent Office. And you see the countries of origin here. There's quite a few from the United States, but Japan and Western Europe are building, and the numbers are building. So you see, it's moving up. People are thinking of more things to write patents about. And then here is a list of the types of product areas that people identify their companies as doing. This is what, if you say, what does your company do? Well, this is what it does. And you see there are some companies, for example, like Nantero, that are focused on intellectual property, making a suite of patents that describe how to build something that can be licensed to other people. And then there are a tremendous number of people who identify, companies that identify themselves, here we down to over 100 that identify themselves as materials companies, that somehow make a material that can be involved in a value-added product. And then note drug delivery therapeutics, a big contingent there. So you see the finished products, the ones that we might normally associate with normal products, are lagging behind, and I think that will grow. This really matches pretty well with Chris's S-curve that he drew before. As we start to build, we're going to see more and more, and eventually I think the product components and the finished products will be the bulk of these things as it matures, as the materials get more advanced and people are able to take the materials and the intellectual property and fold them into the finished products. I think that's what's going to happen.
Brent, I have a question for you.
Yeah.
It's Doug over here.
Oh.
So just go back, actually, if you can go back to that slide where you showed government funding. Maybe it was U.S. right there. So, I mean, maybe in helping describe what is nanotechnology, I think a question that often arises is, okay, we heard that, organisms have been using nanotechnology since the beginning of time. You presented a slide that said that the tools were created in scanning tunneling microscope early 80s, AFM in the late 80s. So then you had the tools, and now I'm seeing, all of a sudden governments are now funding it in 2000. So I walk away and I think, what is nanotechnology, and why are we talking about it now, and why did we start talking about it really in 1999, 2000, where governments are funding it? Why weren't we talking about it in the 80s? I believe that the first reference was in 1974 at an engineering conference. Drexler, of course, made it famous.
57.
What is the nanotechnology that seems to be captivating the world, in this new century versus, 1959, 1980?
Yeah. I think that what's going on is there are a series of advances that have come to the forefront that people are looking at. And you can point to a number of different fields in the area of energy, people are keenly aware of the energy situation in the world. They're looking for new methods. They're looking for new ways. And so having an enabler, such as nanotechnology, that might contribute to solar energy, might contribute to hydrogen economy, that drives people to start to look at these things. Dario, want to say something?
Don't you think there's also the convenience of a label? That, you know, after the dot-com boom, now
We're
you
looking
have
for
the
something.
ability to say, here's another thing, we'll package it, we'll call it nanotechnology. It touches every field imaginable, and
Yeah.
here it is. You know, it's easy. You can sign a nano act. You can have a conference on nanotechnology, right? Foundations can have a conference on nanotechnology. I mean, there's a convenience there.
Yeah, I think that's part of it, is that it did, Hank, sorry.
I was going to say I agree. I mean, we've been doing nanotechnology for decades and decades. It's just that we didn't use a convenient label. In 1972, although there were people who were using it, in 72 I visited a lab in Paris, the Thomson CSF, and they were doing nanoelectronics, it was called. I mean, there's really not something dramatically new here. It's just, as you say, an emphasis on a label.
Yes.
But that gets attention at various levels.
It does
in
get
the
attention.
scientific community, there's nothing particularly new happened.
But that label may be important. I mean, we sort of cynically say we have a label now for it. And, you know, at academic conferences, I've heard it joked that, you know, nanotechnology is what I do and you don't do so that I can get the funding because there's only a certain pot of money. But, you know, when I think of what the biotech revolution was, you know, and I think of a label, I think that was a phenomenal label because think of the dollars that it attracted to solve a problem that was important to mankind. And so it is a label, and perhaps it's even a larger umbrella label than biotech because it refers to everything. You know, there's going to be downsides to that, but one of the upsides is it has attracted a tremendous amount of money to solve scientific problems that could have impacts and hopefully will have impacts.
I think it's confusing to use a label something that doesn't exist. I mean, there are no nanotechnology stores. There's no nanotechnology shelves in any stores. It's simply a thing that doesn't exist at the moment. It's a name for something that may exist sometime in the future, and I personally believe that it will. Currently, it doesn't
Apple
exist.
sells a nanopod.
I'm sorry?
Apple sells a nanopod, so there is a store for nanopods.
Yeah, that's a very good example. That's something that the only thing now about the nanopod is the name. There is absolutely no nano component in this particular product.
Actually,
So
there's flash memory inside.
So at this moment, really, I believe that the use of this label introduces tremendous amount of confusion in people's mind, and sometimes I think it's a misleading confusion. It's the same goes for the nanotechnological revolution. If there is going to be one, this is really the most advertised and previewed revolution in mankind's history. I mean, if the Bolsheviks would have announced their future revolution this way, we would never had a problem with communism. So I hope that we're not killing the prospect of nanotechnology with the misuse of the label today.
I think that without regressing back to Shakespeare and what's in a name, I think there is a way to sort of think about this that might be a little bit helpful, which is, and we could learn from the examples of the internet and of the most recent significant technology, biotech or information technology. You do have this sort of evolution of technologies, as per Clayton Christensen at Harvard, of a platform effect that has to take place before the killer app is created. If you think about the internet as a great example, the most recent example, we were playing around when I was at Carnegie Mellon with ARPANET since, Christ, I can't even remember. I mean,
Civil
I was a kid
War,
back
I
then.
think, right?
But if you sort of think about when internet conferences started happening, and when internet funding started happening and all this crap, it actually happened around era 1997, just around the time that Netscape and Amazon really hit big. Why? What was the internet to everybody? To your point, sir. Email. Email is an actual bullshit app of the internet, if you really think about it. Yet everybody rallied around email, and boom, telecom companies took off, and e-commerce companies took off, and blah, 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 blah. So I think probably maybe we could sort of thread the needle or find a middle ground here that says a label is convenient so we know what we're talking about. But what we shouldn't think too much about is the label could be energy or biotech. The other example is biotech somebody uses. By the way, biotech is nothing until stents came along. You know, Genentech was around for God and heaven knows how long and how much money was put into it, and it never went anywhere. Amgen came along and whooped them based on stents. And so until you don't get to that killer app that people can rally around for right or for wrong, you really don't have a proper label. And if what we want to do is call it XYZ or Carlos, if you want, I'll volunteer my name. I mean, if we just agree that there's a name that sort of is the unifying principle of this body of work, and we can slice and dice it over the next day and a half as much as we want, and then hopefully bring it back together, I don't know, Brent, in 10 years when you do have the killer app, then you'll get real money. And FYI, one last point. If we did that chart for the internet, you know where we would have been? In 1978, when IP was actually first starting to get involved. $8 billion is peanuts, guy. I mean, eBay just bought Skype with this experiment for 4.1. So maybe 10 years from now, we'll look back at this as still scientific, and maybe that's when you'll have the killer app that we can talk about. And flash memory is not the killer app as yet. Cheers.
Right. I mean, I think that that's a good point, and I think to differentiate is if you label nano to cover all fields, it ceases to be useful, right? And there are well-known industries that are well-defined. Like, say, the semiconductor industry, it's well-defined. People understand it. That is not nanotechnology, it's the semiconductor industry. You should still talk about the semiconductor industry. That being said, there might be things, a progression of technology, tools that are used for nano applications in other fields that are developed within the field or are used elsewhere. But if the discussion is nanotech as some entity going to create an enormous new field on its own of equivalent scale to a biotech sector or medicine or semiconductor, that's a different proposition and maybe much longer term.
Chris?
I think that in the academia there's been a lot of nanotechnology research going on. So that's a fact. But there seems to be a sudden creation, influx of the number of private sector companies calling themselves nanotechnology companies. These are in reality companies which are involved mainly in micron level, MEMS, for example, and they venture to think about wanting to go into nano, but because of the tag and perhaps the ability to raise money much easier, they all jumped into the bandwagon. I cannot imagine that all of a sudden there are 300 nanotechnology companies coming up all within a span of 2 to 3 years. So some of it is really a hype and riding upon that wave of just calling themselves nano when they may be quite a distance away from actually producing anything that's useful and commercially productive.
Well, I think part of what's going on here is you can see there are a lot of definitions. There are a lot of people saying a lot of different things. Some of them are right. Some of them might not be right. They're broad definitions. It covers a lot of different areas, a lot of different product specifications. And I think that's really the thing that we're trying to draw out here so that you see what's going on. And we are at the beginning of this. And I think in the next 10 years, to Carlos's point, it may be that we don't even use the word nanotechnology because it turns out that whatever it was good for, whether it be nanoparticles, quantum dots, nanotubes, nanowires, has evolved into its field. So now it's part of a sensor array. And it's just a sensor array. It doesn't need that label anymore. But for right now, in order to unify everyone in one spot, have communication going on, this is what people are doing. And let me explain one reason. I'll get to you, Chris. One reason that I think it's a good thing, and that is nanotechnology, as you can see, involves many different fields and what I call the combinations of disciplines. And in science, it typically is that people, much like in business, are siloed. The chemists stay with the chemists. The physicists stay with the physicists. The engineers stay with the engineers. The medicinal people stay with the medicinal people. Doctors don't talk to physicists. And nanotechnology has provided a platform by which different groups can talk to each other at the same time. This combination of disciplines is evolving. And I think this is critical. And that critical mass of people discussing things will lead to new innovations. And those innovations are going to be incredibly valuable in the future. So I proposed, when I was at Harvard, I told the head of the engineering department, I said, if you were going to do one thing at this school that would make a real difference, he said, what's that? What do you think we should do? And I said, build a tunnel from the chemistry department to the applied physics department, because in the winter in Boston, it's really cold, and we're too lazy to walk across the street and talk to those guys. But boy, if you would make a tunnel, we'd go over there all the time. And he laughed, but a tunnel has effectively been made, and the platform is nanotechnology. And you'll see now, if you go to my alma mater, you'll see the applied physics people are routinely over in the biochemistry department. When did that ever happen? Something special is going on, and it's under this umbrella.
You just made almost precisely the point I wanted to make. So let me just
It must have been good then.
I think it explains, though, a little bit why the scientific community is more likely to say we've been doing this or that or the other thing for years, because this new label is designed to cover the convergence of some things that chemists have been doing, some things that molecular biologists have been doing, some things that applied physicists have been doing. So they all say, we've been doing that, but when you put them together, you get something that people looking from the outside can describe and say when those things interact, they're creating some new properties or some new capabilities that are going to be used by our economy.
I like to say, I love peanut butter, I love chocolate, but boy, you mix those together, that's pretty good. See, I do have good jokes, don't I? Okay, let's keep going here. This is, again, just some diversity. This is really, I think these are the purpose of these slides, is just to give you a sense of this diversity and what people are talking about. And we have had a lot of this stuff for a long time, but we haven't used it in this way. And look at this. Do you have any nice misspellings here? Carlos, do you see any misspellings? But I think these are the targets for nano suppliers. When we say nano suppliers, not that they're going to deliver just a small amount of material. It means they're going to deliver large amounts of material that have nano properties. So this might be nanoparticles, nanowires, etc. But this is where people identify that they think they're going to be delivering. And what you see here, you see everything. You see anything from defense, consumer products, chemicals. There are people doing things all over the place, and that's the diversity. And this takes a whole bunch of different disciplines. There's engineering, medicine, all of these things are built in, and that's really what this nanotechnology is about. Okay, let's see. This is just another way of tracking things that I think you'll agree is very interesting and looks like growth. This is the number of publications, and here's the United States in blue and rest of the world, and it's just going up. People are identifying more and more papers where they call it nanotechnology, and I think that's just good. That just means that we're exploring it more and more. And a lot of these papers perhaps aren't the best. Maybe there's some irreproducible results in here. Maybe we're going to find some things that just weren't important. But within this will be many nuggets of real and excellent work. Here's another measure. These are the so-called high impact. So this is something where they really these articles have appeared many places as references to others. And you see the percentage of these high impact articles which have the word nano in them is going up. And I think that also is an indicator that people are getting this convergence, this combination of disciplines. Now, let me get to I'm going to switch gears. I think everybody understands what's happening here. There's some momentum. It's early, but we're getting somewhere. I'm going to switch gears into a little more technology that I want to bring out. And these are some of my favorite things. So, then I'm going real fast. Okay. Wow, we're going. So here's nanotubes. I'll just go through some of these, which are my favorite things. We talked about folding over of graphite sheets, fullerenes. We talked about Buckminster fullerene, nanoparticles. And what do these all three have in common? Carbon. They're all carbon, fundamentally made of carbon. This is a carbon nanotube. As I said, it's something that's about 20 angstroms in diameter, roughly, but has a macroscopic length. That alone is an interesting thing. And this is a molecule. This is not a traditional material as such. It's not a thin metal layer. It's not a dielectric. It's nothing like something we've seen before. This is a special kind of molecule. These rings are rings of carbon that are interlaced, much like a graphite sheet. And here's some of the properties of it. Strength, 50 times stronger than steel. There are lots of ways to measure that. Hank, don't stop me if you disagree. We can debate it. Current density, these things can handle lots of current. They have tremendous elasticity properties, and they have great thermal conductivity, all made in one molecule, one special new molecule. That's got to be interesting if you can make a molecule that has these nice effects all bundled into one thing. And then there are some other benefits. For example, they're not very dense, not very heavy. They have great thermal stability. I mean, this is in vacuum, 2,700 degrees has been measured for certain kinds of nanotubes. They also have great chemical reactivity, which to chemists mean we can manipulate them. We can do lots of new things to them, and that's a fascinating thing. The downside of some of these new nanomaterials is they're still costly. We don't know how to make them in large quantities. So I estimated that carbon nanotubes, single-wall carbon nanotubes, are about 10 times the price of gold. That's pretty pricey. And I don't have any with me, so nobody try to try anything. But that price is coming down rapidly as we learn how to make these things. And then this is just some graphics that I found, which I thought were just neat that people can understand. So this has come through a 3D sort of looking thing, but these are a bundle of carbon nanotubes, and you can just see how they have interactions with each other. And these close interactions, we call van der Waals interactions, would be very powerful forces. And then here is something called a multi-walled nanotube, and you really get a sense of what it is. Here's a single-walled nanotube in the middle, surrounded by larger graphene sheets to make a sort of a Russian doll structure of nanotubes. And I think that's good. Here are some of the things one can do with nanotubes, or people are looking at with nanotubes. And this, again, one material, one new type of molecule, and there are several different types of new types of molecules available, and look at all the potential applications that people are working in. It's not to say they're going to come up with products in all these areas, but people are looking at them. And that's an incredibly diverse set of possible applications for one new type of material. And that's pretty good. This is a busy slide, but NASA is looking at what they can do in nanotechnology. And I think all you see here, all I want to show here is the diversity of things that they're doing with nanotechnological elements. So they start with materials that are interesting for things like smart skins for a new version of spacecraft that they want to do, all the way down to sensors that they want to use for exploration out to other planets. I know there's a big mission they're working on potentially to the icy moons of Jupiter. And the problem with going out to the icy moons of Jupiter is there are large radiation sources out there. Once you get out there, maybe nothing will work. And so they're looking at how do we survive the trip? How do we have our electronics survive? And they have big challenges if they want to do these kinds of explorations. So that's another thing. This is a slide which is dear to me. I think it makes a lot of sense for nanotechnology. There are various things that happen at the nanoscale which people try to fix. And they say, as we shrink, for example, in CMOS, we have problems. Problems occur. We have different types of things that are issues. But there are also potential exploitations that can happen in nanotechnology. And that's one of the things I meant in properties that will be coming up in several of the talks. We'll see people finding something that you might consider to be a problem and exploiting it, using it for making things. And these are just some of the examples of things that can be exploited. Let me see. Because we went over, I'm going to skip a couple of these. Here are some of the applications that I personally believe will be coming up in the next 5 to 7 years. I think solar cell technology is going to the forefront. People are very interested in it. And Flexible electronics, perhaps. They might be slow, but they might be flexible. People have been working on. Definitely some new work in extended life batteries. There are several companies that are really working hard in battery technology, and that's good because mine are always running out. And then I have to give a plug for myself. I'm working on the Nantero non-volatile memory that I described in the beginning. So here's a market survey of memory. You see different types of memory. And let me just go through. I'm going to give this is just a quick overview. I'm not going to talk about what we're doing right now, but just give you an idea of what's going on. So here's a single-walled carbon nanotube spread over a couple of electrodes. And here it's in its off position. This is suspended over this electrode. And it's high resistance state going from this nanotube down to this metal line here. And if we apply a current and cause the nanotube to deform, remember, it's a molecule, so I'm plucking it like a guitar string. Each carbon atom is being moved a little bit, displaced a little bit. I can bring this in contact and overcome some forces here. We won't get into the physics, but when it contacts this, it's now in electrical contact, and we can read that out as a lower resistance state. And then it turns out, and this goes to Annabelle's question, there are some forces here between the carbon nanotube and this underlying electrode called van der Waals interactions. When you remove the power, this thing remains static. That's a new force. Well, we know about the force, but that's a new thing with a new material. That's pretty good. So that makes it non-volatile. And then we can turn that off, and we can address it in different bits to make a non-volatile memory. And this isn't really what Nantero is making, although we did make this. In order to integrate it into electronics, you have to do a lot more than this, but it gives you an idea of something that can be done with carbon nanotubes. I didn't want to go into too many details. Here's just sort of a view of nanotube work. These are discrete devices. This is a device made by IBM using a single carbon nanotube. And the sorts of things that the challenge of doing this is how do you put these single devices on a big wafer and integrate them? And you've got to figure out how to do that if you want to use nanotube technology. So I'll skip past this, but the way we do it is we make a liquid of carbon nanotubes. We suspend them in a liquid. Then we put them on a spinning device called a spin coater, which has centrifugal force. And what happens is the carbon nanotubes spread out over the whole surface of this thing and make a very thin film. We remove the solvent, and now we have a thin film of carbon nanotubes in which we can work, and we can pattern them and make devices of them. So that's just an example of how one would utilize carbon nanotubes in a way like that. I have it diagrammed here. Here's a fabric monolayer film of carbon nanotubes, and you can see it looks sort of like spaghetti. These are the carbon nanotubes. And we can apply a chemical to it, and that chemical covers it completely. Then we use a lithography tool to expose this chemical so that some of it can be removed and some of it remains. And when we do that, you can pattern lines of carbon nanotubes, and in between these regions are the remaining photoresists. You can remove some of the nanotubes using a process that etches them, that destroys them, turns them into gas, in fact. And then you can strip away your chemical, and you're left with these patterned nanotubes. Here are additional applications and areas that people are using for these. We're working on memory applications, but there are several fuel cell applications, for example, that are making progress. If anybody wants these slides and you want to go through them, I'm going to make them available. So you can take your time and go through, and you might want to ask questions. What do you mean by this, and what's going on with that? And I'm glad to help you. So 19th century, steel was the driver. Industrial revolution. I think we all agree on that. Does anybody disagree on that? Okay. Next, 20th century, information revolution. And obviously, we all benefited from that, although my laptop always gives me trouble. Here's an idea. What if there's a new material? I'll just posit one material that I'm interested in, carbon, and it might make a new revolution for the next century. We may get whole bunches of new devices out of it. Let me quickly go through another example, which I think will have interest to most people. These are a whole bunch of top-selling drugs. Some of you might recognize some of these drugs: Lipitor, Zocor, Zoloft. That's a good one. Plavix. Somebody laughed. Who laughed? Okay. But 80% of these drugs are so-called chiral drugs. And you can see this represents a tremendous value to the pharmaceutical industry. What that means is, if you take a molecule, and this is albuterol, which probably a lot of people know about, especially asthmatics, it has two forms. There's the good twin and the bad twin. Everybody has a good twin and a bad twin every morning when you get up. It's a problem you have. Your right foot and your left foot. Your right shoe fits on your right foot. Your left shoe doesn't fit on your right foot. And that's how we identify the right foot from the left foot. It's not because your mother told you. It's because your shoes actually identify it. And this is a problem in chemistry. We have a right-handed version and a left-handed version of most drugs. So one of them has high efficacy and low toxicity, and the other might have lower efficacy and higher toxicity. It's a problem for separating these two. So here's a company that's made a material which is not a normal nanomaterial. In fact, it's a macroscopic material with nanoscopic pores, and the nanoscopic pores do the work. And here's my combination of the good twin and the bad twin, and I'll animate this. And what happens is the good twins, the good chiral molecules, go through the nanopores, for which it fits perfectly, and the bad ones don't and are rejected by the nanopores. So you can literally filter away good twin from bad twin. This is a major problem in chemistry and pharmaceutical science that is solved. And oh, by the way, they have this, and they can make large quantities of it. So here's a way it works. You take this material in with your compound, or here's your compound. Here's your material that you're going to pour in, and I have nice graphics. Pour it in, and what happens is the good twins don't enter the material in this case, and the bad twins do enter the material in this case, and you've separated them out. You simply just pour it and separate. I think that's a good example of another type of nanotechnology. It's here now. It's not going to be in 10 years. In fact, it's here right now. They're using it with pharmaceutical companies, and it's very handy and affects a big potential market. So now let me talk. This is just for thinking. This is just to get you thinking when you're going through all of the talks today, and you're going to hear a whole bunch of interesting talks. What are some of the barriers? What's the problem that might arise in nanotechnology? Here are some of the ones that culture shock. For example, we talked about this. Semiconductors meet biology. Biologists and semiconductor people don't talk too much. In fact, they speak different languages. And that's going to be hard for people to get used to doing that kind of discussion. Business models. Materials business models, venture capitalists don't like it. It doesn't look like a good business model. How do you handle these new materials? How do you handle companies that focus on intellectual property? What are we going to do with those? And Doug, you're going to talk about that, right? How do you handle things like that? How can you invest in companies like that and make money? That's going to be an interesting thing to talk about, and I think people should think about that throughout the day. Then, expertise. Who knows about this stuff? Who are the experts? How do you call experts? Let me give you an example. My law firm, big law firm in Boston, they came to me and they said, we want to do a nanotechnology practice group. And I said, okay. They said, well, we don't have any nanotechnologists. Do you know where we can hire some? And I said, well, no, there aren't any nanotechnology lawyers that I'm aware of. They said, well, what are we going to do? I said, here's what you ought to do. Go and get the IP lawyer who really works in physics, the IP lawyer who works in biology, the IP lawyer who works in chemistry, the IP lawyer who does engineering, and put them all in the same room and label it Nanotechnology Practice Group. They went and did it, and that practice group exploded. They have a tremendous amount of business. And in fact, having those lawyers work on cases together really was a value add to the customer. And then this is one we haven't talked about yet, but we better bring up because public acceptance is a big deal. If people are thinking, and going back to Hank's point, that these things might be scary. They might be nanobots. They might do strange things that we don't understand. There could be a lot of fear. Example, biotechnology and engineered fruits and vegetables and materials that have come out. Is that dangerous? We don't, you know, I don't know. I eat a lot of them. I feel, well, maybe that's not a good example, but, you know, I eat a lot of them. And then last, and this is a point we brought up before, which is in order to instigate more nanotechnology products, we're going to have to break down some of the silo activities. If you have a group that says, look, I do software and that's it, then how will they participate in nanotechnology? And the answer is we need to have this combination of disciplines where people get used to working together. And I think this is going to change how we do business in all of the world. Okay, and last, thank you. Thanks for listening.
Brent, thank you very much. And thank you all for participating. We're off to a good start. Perhaps for some of you that was a bit of a fire hose to drink from.